Howdy, my name is Joydeep and this is the second part of the video for the MSc 660 Materials Informatics course. The presentation is based on the application of supervised learning in material science. The paper is from Material Science and Engineering at Texas A&M University by Dr. Karman and Dr. Aroave, and it involves both computational as well as the experimental workflow for design and discovery of shape memory alloys. This paper is titled Data-Driven Shape Memory Alloy Discovery Using Artificial Intelligence Material Selection Framework. It outlines a detailed procedure that integrates machine learning, both conventional, supervised, unsupervised, as well as deep learning, with experimental validation to discover novel shape memory alloys with optimized properties for solid-state actuation. This paper was published in 2022, and so far it has 34 citations as of the said date of presentation. To begin, the motivation for finding shape memory alloys is the large transformation temperature ranges, wide thermal hysteresis, as well as poor cyclic stability under stresses. So one of these primary obstacles in the deployment of shape memory alloys in solid-state actuation systems is basically the low efficiency and functional instability due to this transformation thermal hysteresis as well as large transformation temperature ranges during this martensitic phase transformation. So far, the quaternary as well as ternary alloys discovered from the basic binary nickel-titanium system have failed to narrow this hysteresis under the applied stress. So the objective is basically to accelerate this discovery of the noble shape memory alloy compositions and to optimize the processing window to narrow down this hysteresis and the actuation strain. And this is basically materials agnostic procedure that can be applied. This framework can be applied to vast compositional space of material to design instead of relying on these time-consuming experiments. And this using this framework without relying on these vast time-consuming experiments, we optimize the composition. The authors also found a novel alloy that exhibited the narrowest hysteresis and the transformation range. So conventional route is basically, in case of the shape memory alloys, is basically to discover various compositional space using conventional machine learning approaches without relying on experiments and validating the results. This approach basically integrates both experimental as well as computational workflow to design novel shape memory alloys for solid-state actuation. And this is the basic outline for the AIMS framework. Next, we go to the basic highlight where we discuss the computational and the experimental workflow. First, the authors developed the database using various compositions, processing history, test parameters across a wide range of shape memory alloy ni-Ti copper systems. And this dataset was prepared using 6,000 data entries from the author's lab and various supplementary data from the literature. Using this data, they actually post-process the data into 88 features that comprised of 26 functional properties as well as various microstructural features. Then they deployed this AIMS machine learning algorithm, which involves various types of machine learning models that comprises of unsupervised learning, supervised learning, as well as deep learning, and they basically um, split the dataset into 80% training and 20% test. The main highlight of this AIMS model is XGBoost, which is basically a supervised machine learning algorithm, which was used to fine-tune the parameters and find the most important descriptors that contribute to the narrowing of the thermal hysteresis, and hyperparameter tuning as well as the balancing of the data set to remove the duplicates was done using the hyperopt as well as the SMOT. Post ML model training, multi-objective optimization like Bayesian optimization was utilized to narrow down the compositional design space, and the primary objective of this was basically to narrow down the transformation range and the actuation strain. Um, Using this approach, the authors found a single composition, nickel 32, titanium 47, and copper 21, which predicted to have the best properties in that could be used in the solid state actuation devices. And this was experimentally synthesized using vacuum induction melting, and then it was subjected to various post-processing testing like differential scanning calorimetry, isobaric heating cooling, and thermal cycling tests to confirm their application. And these were actually the authors were able to validate the results, and so far they found that this alloy exhibited the narrowest transformation temperature range and highest cyclic stability across all SMA systems that are designed till date. First we go to the basic first we go to the basic idea. Initially, the authors developed a large data set that was part of the author's laboratory for which was developed for like 1.5 decades of 6,000 experimental data points of the nickel titanium system. This was basically supplemented with trustworthy data from the literature comprising of 250 additional data points. And the key highlights of this data is basically the alloy composition, different processing conditions, as well as different material properties that considers the thermal hysteresis as well as the transformation temperature. Post developing the database, the dataset was cleaned to basically remove of the duplicate data as well as the outlier data, and also input some missing parts of the data, like if there was no heat treatment, it was considered to be room temperature treatment. And then there were various descriptors were used to identify the individual data and the properties of the alloy, for example taking into account the thermal history, the valence electrons, atomic radii, and the Mendeleev number. So here on the right, you can see the sunburst charts illustrating the breakdown of the shape memory alloy dataset that has been developed. There has been 88 features that are circled by this green and the blue circles that describes the composition, materials descriptors, and test parameters, as well as processing. And on the right, you can see the 26 material responses, which includes the functional properties as well as the different microstructural features that were taken into account while designing this database. Next, we go to the machine learning framework, which was part of the AIMS framework. They used the XGBoost to basically develop the model that identifies the key material properties for this SMA system. And apart from that, they used extreme gradient boosting, random forest, as well as deep neural network to basically understand and predict the different properties like transformation range, actuation strain, as well as the transformation temperatures. And they use hyperopt and smooth technique to basically tune the hyperparameters as well as refine the imbalances in the data, post which they did Bayesian optimization to basically optimize the material composition by taking into account the narrowest transformation range as well as the best actuation strain. This is basically a multi-objective technique which was used to balance between various objectives in order to yield a specific composition which was of the interest for this study. And on the right, you can see the performance of the trained extreme gradient boosting regression model to predict the martensite finish and the austenite finish temperature, as well as the actuation levels in the night-high based shape memory alloys. Important part is basically the transformation temperature range, which is the difference between the austenite finish and the martensite finish, using the parameter sensitivity analysis feature with the extreme grad boosting regression model. And here, they also use the deep neural network in this ternary nickel titanium copper system to find this range, where they use their test models as well as the training data to fine tune and optimize the single composition for this application. And based on the statistical model fitting, they found that in the two features like the enthalpy of fusion as well as the Mendeleev number had the highest contribution. Finally, they did experimental validation to design this alloy, this novel alloy of nickel 32, titanium 47, and copper 21. They synthesized via vacuum arc melting as well as heat treatment. They post-processed it during hot rolling to elongate the grains, to elongate the precipitates, as well as additional heat treatment for isobaric heating cooling experiments. And here you can see the transformation ranges for the solution heat-treated equiatomic data entries for all the nickel titanium-based shape memory alloy system. In the newly developed data set, it is basically visualized as the function of the two most important material properties, as I reiterated before, which was the Mendeleev number as well as the enthalpy of fusion. And this was found by extreme gradient boosting regression model, which was the supervised machine learning algorithm used. That basically these two were calculated using the simple rule of mixtures, and uh, they found, and here in the outlier you can find the specific composition of interest. Then these SMA system was experimentally validated using differential scanning calorimetry to measure the transformation temperatures as well as the thermal hysteresis, and isobaric heating cooling tests were conducted under varying stress levels to measure the alloy's actuation strain as well as stability under thermal cycling. And also they did thermal cycling tests to understand the long-term stability under stress. Um, and basically we have the box and whisker plots which show the transformation range of various shape memory alloy compositions from the newly developed shape memory alloy dataset, together with also the predicted as well as the experimental results of the nickel titanium copper system using this particular AIMS framework. And you can see that the study which has been highlighted shows the narrowest transformation range, and predicted and experimental results of the nitide copper alloy are basically shown in red. To basically summarize, this paper is a novel paper to understand the shape memory alloys used in solid state actuation devices, and so far they use both experimental as well as computational workflow to predict and synthesize a specific particular shape memory alloy that exhibited the narrowest transformation range, cyclic stability, which matched closely with their machine learning predictions. Thank you.